יש תרגום.
כן, שחצי השני.
לא זוכר את זה.
זה פעם בשבועיים.
זהו,
אלא אם כן אנחנו מודיעים.
כן, כן, רק אבל שאלה אחת, תכלס, כאילו, איך המשפעים מפתחים כל כך
אוקיי, I think we should start.
שלוש זה הבעייתי.
Ready to start the class? Okay. So in the previous lecture we started looking at various operators that are represented by second quantization operators in Fock space, and we discussed one-body operators, which are simple, that are just independent particles, and two-body, which represent interactions. And today I want to discuss some more examples of interaction terms that we'll be interested in looking at and give us a physical phenomena. So let's look at the following example. It's basically interacting electrons in materials. This is one of the main examples where we need some tools to be able to describe the quantum particles, in this case the fermions, and we know that because they have electric charge, they are interacting and sometimes even strongly interacting, and in certain systems the interactions can be the dominant energy scale, so much larger than the kinetic energy. So we want to have some techniques how to deal with it, and of course it is true for any kind of many-body interacting system. So interacting electrons, and the general paradigm is that we have an Hamiltonian that is written as a sum of one body part that usually we can diagonalize in some basis and find exact eigenstates. This is simple, and we have an interaction. And we already discussed one version of it. And this is a good description for conductors or for metallic states of matter, where the electrons essentially have a kinetic energy that is very large, and that's a very large energy scale. So if you remember from your solid state course, the Fermi energy that determines the size of the kinetic energy in electrons in metal is very high, right? Because it's a very dense fermion gas. So it's in the limit that Fermi energy is 10 to the 4 times the energy scale of the thermal energy in room temperature. Okay, so in room temperature, it has like a very strongly quantum gas, and so this is in metals. This is true in metals, and in this case, so if Fermi is large, and therefore the convenient basis in which we want to write H naught will be in K space, right? So we can we prefer to use the K-space for describing states, and usually it's written like this. Okay, this is just H naught. Okay, the sums over K and sigma. So the quantum number for the single particle states and for the creation and annihilation operators is the wave vector. Now,
what is epsilon?
Epsilon is energy, is the kinetic energy of an electron at state K. Okay? And a single particle. Okay, single particle. And okay, so we know actually how the states look. We know how the ground state look. It's just a field Fermi C. And typically, in order to treat interactions, the first thing that we'll try and will turn out to be a good approximation is to assume that V is in some sense much smaller. Okay? Now actually it is not really true in a naive sense, but it turns out that perturbation, we can treat it as a perturbation and do an expansion in powers of V, and it turns out to be a good approximation. Okay? So the approach we will take, and we'll do it in the next lectures, not today, is to take this as your zeroth order Hamiltonian and do an expansion in powers of the interaction. Just perturbation theory as you know it from your undergraduate. You learned it, right? I hope. So we're going to use this as a basis. Now there can be an opposite limit, and this is what I'm going to discuss today. Let me call it in more general, complex materials that typically are not metals. Okay, so they are, for example, heavy element compounds, oxides, actually most interesting materials that show phenomena like magnetism, like superconductivity. I mean, superconductivity you see also in metals, but the more interesting versions of it are in materials that are not metals, and you can find interesting insulating states that are electrically insulating. They are actually dominated by the interactions. Okay, and why is that? Because in some materials, the reason that they are insulating is that the conduction bands are very narrow. You remember, I think, I don't know if you remember this from your solid state undergraduate, but there is a band structure to every material. And if the bands are very narrow, then it actually means that the kinetic energy is very much suppressed. And that interaction can become the dominant energy state. So it turns out that in such materials, it's better to describe, to choose the basis for the single particle states, not as K states, which are extended waves with a well-defined wave vector, but rather as localized site states. Okay, so you have a crystal with some atoms, and the electrons, to first approximation, are closely localized on an atom. Okay, so So the basis, we're going to use lattice site basis, which I represent by an index I. And we define the location of around which each electron is localized by a vector Ri. Okay, so this is the picture that we have in mind, that we have some preferred sites that form a crystal. It is usually good to think of it as a Bravais lattice, if you remember this notion above from solid state. And each site is located at vector Ri. Now, the electron wave function is localized around the atom, okay? But it's periodic crystal, so all the wave functions of all the electrons are the same, but and they're not delta functions. They're not localized exactly on the atom. They have some width, but the basis for describing electronic states are the basis of states that in a single particle notation we denote by I, okay? And phi Ri of R are Wannier functions.
I refers to the specific site.
Yes, I is an index of a site. Exactly. Okay, so it's a discrete set of points that correspond to periodic lattice. And so again, reminding from solid state studies, the Fourier transform of the Wannier functions are the Bloch states, which are the two eigenstates of a perfectly periodic crystal. So these phi i's are not actually eigenstates of the Hamiltonian, right? Because there is some kinetic energy, a little bit. There is some probability to tunnel between the sites. Okay, they are not delta functions, but they are a basis in which you can write the Hamiltonian of a solid material, and this basis corresponds to a limit where which we call a tight binding approximation. Okay, so how do these Wannier wave functions look like? If I'm plotting this is R, and this is some location. Let's think just in one dimension for the moment. R is a vector in the continuous space, and this is the location of the atom. Okay. If I plot a typical form of how the wave function phi look like, it looks usually something like that. Okay. It's the same for each site. That's the whole idea about the periodic lattice, that you have identical copies of such wave functions on site I and site J, but you see, because they are not exactly localized, and they're not delta functions at R equals Ri, there is some matrix element or there is some there is a matrix element that can relate, can give you a hopping between site I and site J. Okay, so if I'm writing I take the single body Hamiltonian, which just describes kinetic energy plus periodic potential. If I take its matrix elements between different I and J, I will get something non-zero. Okay, and I can write the Hamiltonian as a matrix in this basis. Now you can diagonalize the matrix and you will get Bloch functions. But for our purposes, let us not try to diagonalize H naught and just write it in its simplest form. Now, this is actually a counter to what we usually want to do, because you say, okay, but we know how to diagonalize it. Why not start from a basis that is good for H naught? The reason is, if I want to introduce interactions that are bigger than the kinetic energy, then it's better to work in a basis that is simple for the interactions and not for the kinetic energy. Okay? So, real space, the site index, is a more convenient basis, although it doesn't diagonalize H naught. And therefore, sometimes it's useful to treat H naught as a perturbation and not the interaction. Okay? Okay, so what I want to do today, yeah?
Experimentally speaking, do we even care about H naught? Like,
oh yes,
we
we care about it very much, because actually a lot of interesting phenomena will come out of the interplay with this H naught. Because if the wave functions were completely localized on the site, right? If they were delta functions, then okay, the interaction would give you something, but there will be no magnetism, for example. All the magnetic phenomena are coming from interplay of kinetic energy and interactions.
Yeah,
okay?
But it's the baseline of it. When you actually make the measurement specifically in magnetism, for example, you see the pattern that we've seen in class, we've seen the scatters patterns, and those patterns are what really
No, right. So
for us.
you're not talking about
Experiment specifically.
Yeah, in the experiment, what you see is the state that is indeed the solution, or if you like, the solution of the full system, which has this and this. What I'm saying is that if this was completely zero, then you'd get different states. There are some states that
not only with a delta of some energy.
No. Okay, so yeah. So and actually you will see some examples of this, some of them in the tutorial, in one of the next tutorials. Okay, so what I want to do today is to write down, first of all, I'm writing H naught, and I write H naught in the so-called tight binding approximation. And you see, we also have in any solid material you have energy bands, but let's now, for simplicity, just focus on one band which plays a role because the chemical potential is inside that band. Okay, all the others are separate by energy gaps and they're not playing any role. Okay, just one. So we have just one band, and we write H naught in a tight binding approximation. this is what it looks like. Usually it has some local energy. Okay, so which we can write as okay. So this is a site, so-called the site energy. So this describes the energy of an electron that is exactly localized on the atom. And because it's a periodic crystal, this epsilon does not depend on the site. It's exactly the same for all of them, okay? And here we have a sum over just terms that are diagonal in the site, where now our creation and annihilation operators, they have two labels, the site index and the spin. Okay, we still always have the spin. The spin is up-down. It has two states. It's a spin half particle. Okay.
But that won't work in cases of like boundaries.
Wait. What do you mean boundaries?
For example, the effect that happen on the boundary, and it won't work because this is in symmetry. Like
this assumes an infinite crystal.
yeah, so
yeah.
in the boundaries it just won't work.
Right, but I remind you again and again that in this course, or at least in the next months also, we're not interested in boundaries at all because we are talking about system of 10 to the 23 particles, okay? So the boundaries are not interesting, okay? So, we of course assume an infinite system, but this is only the local term. Now there is a second term in the energy that we characterize by a parameter called T. And here we have a sum over ij, where this notation describes nearest neighbors. Okay, this is nearest neighbors. And here I have, and of course sigma. Okay. This is the way I'm writing it here is actually. I think I don't even need to write it because let me just write it like this, because if I'm summing over all nearest neighbors, then each site appears once as an I and once as a J, so it's Hermitian. Okay, it should be an Hermitian Hamiltonian, of course. And this T is called hopping coefficient. And this actually accounts for a kinetic energy because it describes what is this term describing. It describes just a process where for each term here describes a process where there are two sites, I and J, and I have some probability to hop between I and J. Okay? And the amplitude, T describes the amplitude for such processes contributing to the energy. Okay? So this describes hopping, and in fact, this is
describe the probability of hopping?
It's not probability, it has units of energy. So it describes the matrix element of the kinetic energy between the Wannier states I and J. That's what it describes. Okay? In fact, this is exactly what it is. Okay, so if you take, you just compute it. Okay, where H naught is just, you can write it if you like as kinetic energy plus potential, just the Schrödinger equation. And you calculate a matrix element between different or nearest neighbor sites. It gives you some number, some complex number generally, and this is T. Okay? Actually, the convention is T. In fact, it can be a complex number, right? Because only the actually, okay. Let me take it back. If I write the Hamiltonian like this, its Hermitian only provided that T is a ring. Okay, because then you want exchange of I and J should give you the Hermitian conjugate. Okay? Why do I put here a minus sign? The convention is to choose, if you want to choose T positive, you choose it such a way that such a term reduces the energy. So the electrons benefit, they gain some energy from hopping from side to side. Okay? But this is just a convention, it's just a parameter. Now, why is this an approximation? Because here I count only for nearest neighbors. Okay? In principle, if I want to write an exact representation of H naught, I also have some matrix elements between next nearest neighbor and next nearest neighbor. But because, again, we are talking about materials where the hopping or the overlap between electrons at different sites are exponentially decaying, the next terms in this expansion will be exponentially decaying. Okay? So in principle, I can have here a higher order, like if this was my lattice, then I have this T, and I also have T prime, okay? But T prime is typically much smaller than T. Okay, just because, and it's exponentially decaying with the distance. So in the tight binding approximation, we just take the leading one, and sometimes we can have more complicated crystals where we want to account for a higher order, but that's it. So in fact, H naught is actually just this term, okay? The first term is actually not interesting at all, because if you look at it, it's some constant times an operator that sums over all I and all sigma of A dagger A. What is A dagger A? How did we? This is, how did we call it?
The number operator.
The number operator.
If it's a closed system, it's constant.
Right. So exactly, if it's a closed, if it has a fixed system with a closed system, you are right. It's a constant. If it's in the grand canonical ensemble, it's just. You have some chemical potential, and epsilon is just redefining the zero of the chemical potential in a sense, okay? So this is just the total number, and because of that it's not interesting, and we can, for most purposes, just set it to 0, okay? So, so to cut the long story short, let us assume that H naught is just this one term. Ij, and the sum is over all nearest neighbors, and we also sum over sigma, ai dagger sigma a j's. Okay, this is H naught. And of course it's not diagonal, okay? But we just keep it like that, okay? And now we write the interaction, and we want to write the interaction in this basis, in the basis where the quantum numbers of the particles are I and sigma. Okay. So now I'm going to introduce three types of, so first of all, let me write the general expression for the interaction, and then we classify various interaction terms which have different meaning or different effect. So I'm writing the operator VEE in the same language of second quantization, and because it's interaction, it's a two-body operator which describes processes where you scatter two particles from one state to another, and altogether you have four operators, a sum over four operator things. So we can usually write it as a sum over four indices of lattice sites, I prime, J prime, and we also sum over two spin indices. And the term looks like this. So for each I prime, J prime, there's a coefficient that we denote as I prime, J prime. Let me just make sure that, yeah, this is the convention we always wrote. So this is just the most general, almost the most general. You notice that here I'm assuming that the coefficients of the interactions depend on the lattice sites, but not on the spins. Okay, why is that? Because I'm assuming that it originates from something like a density-density interaction, and the density operator, or the number, okay, so it describes interaction which originates from, I remind you something like this. I have some V of R prime, and I have densities, local densities, and the density is a sum over spin of psi dagger sigma R psi R. Okay, so the density sums over all the spin. Okay, it doesn't flip the spin. Okay, and so this is what we are assuming, and therefore what we have here is the following expression. This is J prime sigma prime, Aj sigma. Okay, this is the way I want to write the interaction in the most general way. And we describe it as a diagram because each term here, first of all, has a coefficient that, of course, describes the strength of this type of interaction. And it describes a process where we destroy two particles, one at site J and one at site J prime, and recreates them at I prime and I. And notice that we are assuming that in this scattering we don't change the spin. Okay? So let me maybe plot it. So you're taking a particle from site J with spin sigma and another particle at J prime sigma prime. They are colliding via the interaction. So this is determined by the coefficient U. And then this electron with spin sigma hops to from site J to site I. And this electron from site J prime to site I prime, but maintains the spin. Okay? Actually, let me maybe draw it a little. So suppose these are the sites I prime. This is very general. J prime. Okay. So you are describing a process where simultaneously an electron goes from site I to from site J to I. Okay, an electron with spin sigma, and another electron from state J prime to I prime with spin sigma prime. Okay? And this happens together, okay? In most general case. Okay? Now, what is this coefficient? This just follows from the definition that we learned in the previous class. This matrix element can be expressed in terms of some integral over the interaction. Because again, originally, it all comes from this, but where we represent the density operators in the convenient basis, okay? So what is a ui I prime, j prime? This is a definition. There's a factor of 1/2, and then there is a double integral over r prime of phi ri star at r, phi star r prime, where this can be, okay, hope I have enough space. Actually, I'll write it in a way that can be seen on the board. So, ui I prime j prime is 1/2 integral, double integral on space. There is the wave function in R, the wave function R prime, this is R prime, here we have the interaction, r minus r prime, phi r j prime, r prime, phi r of r j, where these functions are Wannier functions. Okay, they are these functions that look like they tend to be localized on lattice sets. Okay, and V is the interaction. For example, actually in reality, we want to think of a Coulomb interaction. Okay, it's just E squared over the distance. Okay, this is what it is. And now, why am I saying that this lattice site is a good description for the interaction, or it makes it easier to understand what it's doing? Because you see here we have infinitely many terms, right? Because I prime, j prime can be anything. It can be a lattice site here and here and here and here, okay? But if you look at the size of the coefficient, how do you think they depend on the distance between the sites? What do you think?
It decays with larger difference.
So it decays, and in fact, maybe it even decays very fast, because if you're looking at two such wave functions, if you plug into this integral wave functions from different sites that are very far apart, more than 1 unit cell of the crystal, then the integral will decay exponentially. Okay? So in fact, of all these infinitely many possibilities to choose the indices, the dominant ones are going to be from cases where either all the indices are the same, namely really local interactions on the same atom, or nearest neighbor, okay? Right? These are going to be the most important ones, okay? All right? Okay, very good. So therefore, I'm going to account for 3 types of interactions, 3 types of terms, okay? And we'll understand what each term describes physically. And they are going to be the ones that usually people take into account in the model and neglect all the others, okay? All right, so let me erase this. And now I'm starting with the first type of, so we have interaction terms. And the first one I call direct or Hartree. Hartree is after a person named Hartree, okay? So, and what is it? So, the Hartree term corresponds to the case where I have the coefficient is Uij, ij. Okay? So instead of 4 different indices, I have j equals I and j prime equals I. Okay? So let me just call it, there are only 2 indices. But of course, the coefficient u has 4 indices, but 2 of them are duplicates, okay? Okay, so let me also give it a name. because it depends only on two indices, let's call it Vij. Okay? Okay, that's just a definition. Now, if you look at the definition of, the general definition of the matrix element I prime, J prime, it's this integral, but now I'm going to put here, to equate this to the same index and this to the same index. Okay, so what do I get? I get something that, sorry, something very simple. So it's actually okay. So if this and this are the same, it's just the wave function square, right? Absolute value square at R, and the same with Rj and R prime square. Now, because this is only a function of R, I can move it here. So I can write it like this. It's 1/2 of the integral over this wave function square times a separate integral over R prime of the other one. Okay? Now, in fact, what is this? If this is a normalized wave function, it's just one, right? So actually, now if you look at the term in the interaction that corresponds to this coefficient, what is it? It's nothing but, sorry. No, okay, sorry, it's not, that this is not right, because I still have, yeah, it's not exactly, but I have here the interaction term that I still have to integrate over, right? So it's not just two separate integrals. This is what gives it some number. But anyway, you see that it's really an interaction that comes from, it's something that has a very clear classical analog. We have a particle at I, a particle at J, and their densities are just simply interacting. And if I look at the term in the Hamiltonian, which I call, let me put here an index H for Hartree, okay? So this is V electron Hartree. Okay, that's the term. It looks like it's a sum over Ij of this Vij, and then using this general expression and equating this I to this and this J to this J, I get just Ni times Nj. Where notice that Ni and Nj, each of them is actually a sum over spins. Okay, so Ni is a sum over spin indices of A dagger I sigma, A I sigma. So it's just the total number, it's the total number of particles on site I. And Nj is the total number of particles on site J. And this looks like a simple interaction that has a very simple classical analog, right? You put some charge here, and they interact, and this describes the strength of the interaction. So it's a very simple term, okay? So let's leave it at that. That's the Haar tree. That's called the Haar tree. Okay? Now, what is the second term that we are going to account for is called exchange term. That's more interesting.
Different terms can like happen together, right? They are not exclusive.
They're not. That's right. Yeah. So in the sum of all possible indices, you have some terms that belong to the direct sector, some terms that belong to the fork. They all exist. That's actually very important because we'll soon see that the second type of interactions I want to discuss has a contribution that partially cancels the one that comes from the direct. Okay? So, okay? Now, by the way, if you look at the form of the Haar tree interaction, usually doesn't care what kind of particles they are, whether they are bosons and fermions, because the interaction only tells you the information of how much you have here and here, okay? It doesn't care about the statistics, okay? And if it is a repulsive interaction, we try to push them apart. And in fact, if you have a repulsive interaction between particles on different sites, sometimes if this term is very large, what it wants to create a ground state where the particles are localized at the site, okay? Okay, and they want to avoid each other as much as possible. Okay, and this kind of state will create something where the electronic state is itself something that looks like a crystal. Okay? Okay, so that's the direct. Now let's go to the second one. I just want to maybe to write here the general form, because we take special cases. So it's a sum over I prime, j prime, sigma prime of this is the most general. Very good. So that's the second term is called exchange. Or fork. Okay. More. Yeah, so just by the way, once again to create a picture, if I want to describe the processes that are taken care of by the direct interaction, we see that it corresponds to processes where I have electrons on one site just remain there, electrons on the other are remaining, and there's it doesn't involve scattering from one side to the other. Okay, it's just coupling to the number operator. However, the exchange term is something more interesting. It corresponds to the matrix elements, or to the processes where again you have two indices, just I and J, But notice that it's ij, ji. Okay, I actually I exchange two indices in the annihilation operator. Okay, let me write how it looks. What is the operator that couples to this coefficient? It's VEE4. It's sum over I j sigma sigma prime. Notice that here I keep track of the spins, and let me call this coefficient okay. I'll just call it Jij. Okay, I give it a different name. So this is what it is, Jij, and now what is the process? I have I'm taking the general form and just plug in. Two indices are the same. I mean, out of 4 indices, there are 2 pairs that are the same, but they have an opposite order than what I have here, right? Actually, maybe to make it more clear, if I take this operator and I write it more clearly in terms of A and A dagger, how does it look? It's a sum over sigma sigma prime of A I dagger sigma, A J dagger sigma prime, A J sigma, sigma prime, and sigma. This is what it is. Okay, if I write, if I just plug in the expressions for n, and there's a reason why I bother to write it like this, because you see what I have here in the exchange term is very similar, except I take these 2 operators and I switch them. Okay? So let's write it down. So it's J sigma prime, and here I have I sigma prime and A J sigma. Okay? Okay? I exchange the I and J, not the spins. The spins I maintain in this order, okay? To keep the same definition. Okay? That's important. Okay? Now let's understand what is this process describing. So I have my 2 sites, I and J, and what is this operator describing? Each term in the sum describe a process where I take an electron, I destroy an electron with spin sigma at site J, and I recreate it in site I. Okay? So this electron doesn't change the spin, it's the same electron, but there is a hopping process that okay, this is described by, this describes the operator that, let me mark it in a color blue. Okay, this is what it is. We take an electron from site J to site I without changing its spin. Okay? At the same time, at site I, we have some other electron with spin sigma prime, and it jumps to J. So now you see why we call it an exchange process. Okay? So this is what it does. So it really describes a process where you have, it's really, now it is really a scattering process. It's not just interaction between densities. It's a process where simultaneously one electron jumps from here to here and one from here to here. Okay? Okay. Now, notice that, remember that we are talking about creation and annihilation processes of electrons, which are fermions. So, at first sight, it looks like, why is it different from the director? Why is it different? We could maintain the same order of the lattice indices by exchanging between these two annihilation operators, right? But doing that will also change the spin from sigma to sigma prime. But it is mathematically correct, right? Because I can take this whole term using the fermionic anti-commutators. When I is different from J, okay? So if I take this term and I just switch these two, I get a minus sign. So this is equal to, where's my eraser? This term is equal to minus AI sigma dagger AJ sigma prime dagger AJ sigma AI sigma prime. Okay? I'm always allowed to do it to write it like this, and now it is not new information, but what you notice here is if sigma is different from sigma prime, then it's really a process that is not included anywhere in the terms of this type, right? But in the special case, so of course when I sum over all sigma and sigma prime, there are two options, either sigma equals sigma prime. In fact, there are four terms, right? Sigma equals sigma prime, the up, and down, down, or up, down, okay? The first option, that sigma equals sigma prime, is quite interesting because you notice that such a term is the same sigma, so the same sigma, just different different sides, okay? This is the special, out of these four options, there are two of them have the same spin. For the same spin, such a term also exists here, right? Exactly such term, right? So among these terms, the one with the same sigma is IJJI, okay? And it's the same as here, but with a minus sign, okay? So therefore, why am I mentioning it? Because if the interaction is repulsive, for repulsive interaction, all the coefficients U are positive, right? In the direct term, you get some positive contribution to the energy from all these terms, but in the exchange term, the overall coefficient is also positive, right? All the matrix elements, they're all positive, okay? If it's a repulsive interaction, but because of the fermion statistics, if I rewrite it in the way that I'm exchanging two indices, I pick a minus sign. So a repulsive interaction has a negative contribution that partially cancels the repulsive interaction if the spins are the same. Okay? So let me repeat. This is, now it's physics, not mathematics. So if we bookkeep all the contributions, we see that there is, for fermions, of course for bosons it's the opposite. Okay? For fermions, there are particular contributions in the exchange terms that partially cancel the contributions from the direct terms. As a result, the system can gain energy by arranging that the electrons will have, or nearby electrons that are on close sites will have the same spin. Okay? So if you throw your electrons into the lattice and allow them to occupy sites with any spins they like. Two electrons that are close in space where you have a strong interaction because they're very close to each other in space, the distance is small, then they prefer to have the same spin.
Dependent on the sign of the gem.
Yeah, then the sign, as I said, the sign is always positive. Okay, because the original interaction, the microscopic interaction, is just Coulomb. It's repulsive. Okay, it's just the same charges. So, so this is a very interesting observation because it suggests that if you have fermions in a lattice or electrons in a lattice where the interaction is a very dominant energy scale, it would, and they suffer from repulsive interactions. They try to avoid each other, but they also have the degree of freedom of the spin. So they prefer to organize themselves with the same spin. And what do we call this state? State where all the particles, all the sites have electrons with the same spin. That's a ferromagnet. Okay. So this is one mechanism. This is a mechanism for creating ferromagnetism, and it's something that we can. You will show in your tutorial or in the homework, I'm not sure, one of them, you can show mathematically that you can rewrite such interaction term as Heisenberg interaction for spins. You know what is the Heisenberg model for ferromagnets? You saw it, maybe? Okay, maybe you will learn it, I hope, in statistical physics, in the StatMech course. But it is, intuitively, it's just a formulation of what I'm saying now, that there is although the interaction comes from electric interaction, okay, it's Coulomb, it's not magnetic in any way on the microscopic level. Because of the Pauli exclusion, it tends to create something that looks like magnetic interaction, namely it prefers ferromagnetism. Okay?
Kind of looks like the Ising model.
No, not. Why Ising? No, Ising is when you have just one component of the spin. But actually, you will show in the homework that if you use the definition of the spin operator, you can convert this to representation in terms of S dot S. Okay, just nearest neighbor spin interaction, and it's ferromagnetic. It has a minus J. Okay?
What
Yeah?
happens if we convert it to momentum space?
It's not useful. Okay? Then you get a sum over 4 indices of K. Okay? That's why I'm not using momentum space in this lecture, because it's not useful. Okay? You can write it, of course. You can always write. Actually, last week I wrote a general expression for the interaction in K space, and it's still true. It's still true, but it's not helpful for classifying interactions in this way. Okay? Is that clear? Okay. So I want to stress that unlike the direct term that I said has a simple classical analog, it's just density. The exchange term benefits from quantum mechanics, so it doesn't have a class. This effect that you have a slight, actually a change of sign because of the statistics, is special to fermions. Okay. Okay. So very good. Now I'm coming to the third type of interaction terms, and in fact this is the simplest of all three. So let me call it number 3. This is on-site or Hubble, also named after a person, on-site interaction. What is it? Very simple. So out of all possible terms here, there is one where all the indices are the same. Just one site. It's on site. So it is I. Okay, all indices are the same. And you can therefore just define it as a single parameter. Why a single parameter? I mean, in principle, I could define it as U of I. But because we are talking about periodic crystal, then all the UIs are the same. Okay? Just like the on-site energy. So I define here a parameter that I call simply U, and there's a factor of half for convenience because of a reason you'll see soon. Okay, so this is just a definition. There's one parameter that describes the process where all the creation and annihilation operators are with the same site. It's on site. So what is it describing? site is given by, you can write it as U times sum over I, but you still have sigma and sigma prime of, sorry, let me write it with A dagger A, so it's I sigma prime, AI sigma prime, and AI sigma. Very simple. But here you see that A dagger A of the same I and sigma is nothing but a number operator, right? And A dagger I sigma, AI sigma is also just a number operator. So if you sum over sigmas, you can actually write it like this. So it's actually before I do that, okay. So when I write it like this, I sum over sigma and sigma prime, and you can have sigma equals sigma prime or sigma different. What happens if sigma equals sigma prime?
It's just the self energy.
No. What happens is, so notice that all the site indexes
Oh,
are
it
the
will be
same.
0.
Then it's 0. Why is it 0? Because AI dagger sigma square is 0, right? So I'm reminding you, these are fermions. This operator is identically 0. Okay? So in fact, I'm allowed to write it like this, but there's actually only there's only a contribution from, actually let me be a little more careful. Here I have a factor of 2, sorry, because this is how I define it, as a factor of 2. Now, the sigma equals sigma prime is 0, identically 0. So the only contributions I get is if sigma is opposite of sigma prime. And I have 2 such terms, up, down, down, up, right? And both of them actually give the same. It's just the product of ni sigma, ni up and ni down. So this is why the factor of 2 cancels, and I get a sum of I of ni up, ni down. Okay? Very simple. So it's again a density-density interaction, but it's between 2 electrons that reside on the same atom, the same lattice site, but with opposite spins. Okay? So now, and if the coefficient is repulsive, if it's positive, it's a repulsive interaction. What it means is that if I have a lattice with a number of electrons that is smaller than the number of sites, it costs energy to put 2 electrons on the same site. So 2 electrons of the same spin cannot sit on the same site. The Pauli excludes it. But 2 electrons of opposite spins can occupy the same site. It costs energy. Okay? Okay, so this kind of interaction is actually playing a very, very interesting role in materials that are not simple conductors. Not because of this term alone, because this term alone is very simple, it doesn't do much. But if you add the kinetic energy, the part that we already erased in the tight binding that does the hopping, you get a model that is the so-called Hubbard model. Okay, so what is the Hubbard model? It's basically you take the tight binding single body sigma A I dagger sigma A J sigma. This is the single body plus the on-site interaction. Which is just an interaction that give you an energy cost if you try to occupy the same site by 2 electrons, one with spin up and one with spin down. Okay. Why is this model interesting? Because I mean, it looks very simple, but of course, in 2 dimensions or more, it's not exactly solvable. Okay? And the interesting regime occurs when the parameter u is much larger than t. So when the interaction dominates. Now there is some simple exercise you'll do in the tutorial, which shows that because of the interplay of these 2 terms, if I treat the hopping term as a perturbation, so it's the opposite of what we said, we have a ground state that is dominated by this interaction, and it prefers to have 1 electron per site, or 2 now, depending on how many electrons you have in your lattice. But the hopping between 2 different sites can be treated as a perturbation. And then you can see that if you treat this to second order in perturbation theory, you get an anti-ferromagnet. You get a phenomena where actually, if you put electrons on opposite sides, on different sites, they prefer to be oriented with opposite spins. Why is that? You cannot see it in a simple way, but it comes out. The intuition is that the hopping term allows you to gain some energy if you allow an electron. Let's say you have 1 electron here and 1 electron here. If they have the same spin, they are stuck because there's no, right? You cannot occupy the same site with the same spin. So they are blocked from moving. But if you have electrons with opposite spins, in principle, this one is allowed to jump here, okay? But this will cost energy, so it will like to go back, okay? In a second order process. And by doing this, he will gain energy, okay? So therefore, the ground state of an anti-ferromagnetic orientation will be lower in energy than the same spin. Okay. So once again, you can get a state which is magnetically ordered, but in a different way than the other type of interaction. Okay. So. Okay, so all these phenomena you can get from writing this distance. Okay, so and these are the 3 different kinds that we want to maintain in a model. And typically, the on-site is for the same site, and the direct and exchange are usually interaction terms between nearest neighbors, okay? And all the other possibilities are usually less important. unless, in some cases they can get important if you have a very strange crystal or if you have interactions that are partly repulsive and partly attractive. You can get all sorts of complications, but these are the ones that are most important. Okay? Okay, so in the last 5 minutes, let me just start something that will continue, of course, next week. So in all these examples that I gave, you get, if you write a Hamiltonian that includes a 1 body plus 2 body, unless there's a very magical special case, this is not a solvable problem. You cannot solve it exactly analytically, okay? Because one basis will be useful to diagonalize H0 and one basis for the interaction. And there's no basis that at first sight can diagonalize both, okay? In the general case. So how do you proceed? How do you solve the problem? You have to make an approximation. And the approximation we want to do is to do perturbation theory or on one term or the other, okay? What is perturbation theory? And so for that you need some general approach that will allow you to compute the corrections to the Hamiltonian in perturbation theory. And I remind you, if, for example, you have some H0 plus perturbation, okay? And you want to use V as a perturbation, what is the approach? First of all, you diagonalize H0. So you find some eigenstates that solve the Schrödinger equation. And this is in general, right? And it's also true for the many-body case. And we know that if H0 is a single body, this is an easy problem. You just need to find the right basis, and you find the psi is some kind of a Fock state. Now I want to do perturbation theory on V. What is the calculation? The first order correction, anybody remembers? What is the first order correction in perturbation theory? So the correction to the energy, not to the state.
It's just we apply the observable of the correction operator.
Exactly, right? So the first order correction will be just this matrix element. It's expectation value in the eigenstate of H0, okay? And second order will involve a sum over matrix element square with the energy denominator. That's more complicated, but in any case, we would like to, if we just want to take the leading correction, we need to be able to compute such expectation values, and we want a general prescription how to do it efficiently in second quantization. And in second quantization, any operator can be written as a product of creation and annihilation. Okay? So I want now to define, let me just make a few definitions, and we'll stop here and continue next week. I want to do the following approach. Let's define our state psi as the vacuum. Okay, I told you last week, and we saw also an example, that a vacuum state is a matter of choice. You can choose a state let's say the ground state of H naught to be the vacuum, and define creation and annihilation operators according to this vacuum. So let's just call it a vacuum, and this will be a vacuum operator. And now what we want to do is to compute a vacuum expectation value of some operator. Okay? And that's the question. That's the mathematical question we want to answer. The first observation we want to make is that any operator will be can be generally expressed as a product of many operators, A, B, C, D, okay, where each of them they belong to a set of creation and annihilation operators. Okay, they belong to a set of some where A and A dagger are defined with respect to this vacuum. Okay. Now, for any such operator, I can define something that is denoted like this with two column dots, and it's called normal order. It's a normal order of O. What is the normal order? I take all these, so this generally it's a string of A dagger A dagger, A dagger, okay? Lot of things. Now I'm rearranging them by writing all the, there's a product of all the creation operators, a product of all the annihilation operators, and so I put all the annihilation operators on the right in order to reshuffle them so that I will get this form. I must make exchanges. So I pick here a sign that is either plus or minus. Zeta is our usual either plus or minus for bosons and fermions, and it's zeta to some power, some integer which counts the number of permutations. Okay? So if it's an odd permutation, it's a minus sign. And if it's an even permutation, it's plus. If there are bosons, it's always plus. Okay? But it's not important because it's just a phase factor. Okay? Now, so this is this form is a normal order of the operator. Okay, that's a definition. It's a definition. Now, why do I want to write an operator in terms of normal order? Because if I apply it on the vacuum, what I get? 0. Okay? So the normal order of any operator is defined in such a way that its vacuum expectation value is 0. Okay?
But the normal order is not equivalent to just one term.
No, it's not one term. There are no terms. First of all, there are no terms. Okay? There's one operator. And this is just a definition. For each operator, you give me an operator, I can write.
No, but if, for example, your operator is, for example, composed of some kind of place operator and momentum operator.
No. So there are no momentum. The operators are only.
No, yeah. So you want to write it as the ladder operators. You write it as the ladder operators, then you get terms. Now, when you want to get to this form.
this
get more
my definition of an operator will be just a product of some set of A and A data. That's my definition.
That's an assumption.
But-
You can't
No, it's
provide-
not an assumption. You are right. A more general operator, I can write as a sum of such things.
Yeah.
That's right. That's right.
So
But
you choose a specific
I'm
operator.
referring to a particular,
Operator. Okay.
that is just as I said, that all the A's and B's are either A and A. Just a string of some. You're right that if we have many tabs, we'll treat them one by one.
Okay.
Okay? That's exactly right. Okay? Okay, so I think maybe that this is a good place to stop. We are going to next week. We are going to show you how to use this definition to get an efficient way of computing expectation value. We'll derive a theorem that will give you a general formula that and it's going to be very useful for doing perturbation theory. Okay? So let's stop here and I'll see you next week. כן.
אולי להפנות אותי לפרק ספר כלשהו שנמצא בפתוח הזה? יש את השני ספרים.
איזה מהם? אתה מדבר על מה שעשיתי קודם, ההאברד ו...
שני ספרים.
הספר של האלטלנד, זה. אז כל מה שאמרתי על האקסצ'יינג' ודירקט וזה, אז יש את זה פה, אפילו עם אותם נוטיישן.
זהו, השני זה אמור להיות פה.
לא, זה הרבה לפני זה. רגע, לא. כי כאן זה כבר, כאן כבר יש תורת הפרעות. אני חושבת שזה אפילו עוד קודם, זה כנראה הפרק הזה. אני לא זוכרת, אבל זה מופיע בספר, אבל בכל מקרה יש את זה גם ברשימות ההרצאה שלי, ויש את זה בהרבה מקומות, ויש את ההקלטה של השיעור, אז כן. אוקיי.
מה המשפט?
זהות, איכשהו הוגה את השם של הבחור הצרפתי האחרון.
זה פתאום...
השם ארז פשוט מאוד מבולבל, זה בטעות ילבן שני שמות של שני משפטים וקרא לזה. אבל בדרך כלל...
הבנתי למה אתה מתכוון. זה בול אותו דבר, נכון?
זה
זה משהו קרא לו פיתגורס בכמה ממדים?
כן, בתכלס מה שקוראים פיתגורס וכמה מילים זה פשוט... זה לא למקדמים, זה לא...
אני הולך למיקרו, אתה רוצה לבוא איתי?
מי שיש לי לא כל כך דורש חיבור.
אתה יכול לעשות.
כל כך דורש רצון. החזקת אותה פתוחה היא פיזית נשארת פתוחה.
טוב, בדרך כלל, כאילו נגיד מתי אתה פרעה?
היום?
כן.
7:30 בבוקר.
כן, אני מקבל אותך, כאילו לא 7, בערך 11. זה כן יותר מאוחר. עדיין הגיע הזמן כאילו, עבר... וואו, עבר רק 5 שעות.
לא, אני ממש לא יודעת.
לא, עבר 6, כמעט 7 שעות.
אתה אבל מצליח טוב, אלה לא היו קשים, הראשונים היו יותר קשים.
האמת שאני בבעיה.
מה? אתה בא לברוקס ועושה את השיעורים של... אתה בא לניר לב?
לא, לא.
לא
פחות או יותר.
ניר לב יותר טוב באמת.
הבעיה שלו קשה יותר. וואלה לג'יט זה הבעיה היחידה. אבל שתבין, כאילו הייתי אצל ניר לב,
נו.
בזמן שברוקס לימד חומר אחר מן הסתם, ולא היה לי איך להשלים את החומר האחר. כלומר, אני קצת...
אין לך כל כך... באמת שאין שם... הוא לימד הרבה... מה זה הרבה? אני חייב להגיד שההרצאות, כאילו, לא יודע איך, אבל רוחמן הספיק המון בשיעור. בדרך אולי היא מזוויעה, לא הבנתי אף מילה שהוא אמר, אבל הוא הספיק הרבה. ברוקס, הוא מספיק.
אני אוהב את זה.
אבל זה אומר שבסוף הוא פשוט יזרוק עליך מלא דברים.
אולי.
אני באמת לא מבין מה אני לומד ב-3.
למה, מה הבעיה?
לא, כאילו... נניח שאני לא אני, כי מי שאתה מכיר אותי פה, שאני פיזיקאי או מהנדס.
אוקיי.
מה אני לומד שם שלא ידעתי קודם בחיי?
זה כאילו, מן הסתם כאילו. אנחנו יודעים את כל החומר כאילו במדק.
אני גם די, תמיד, אני גם די פורמלי עם עצמי. אני לא חושב המשפט שלו משנים כל כך את הדרך שבו תעשה חישוב במשהו. רגע, עידו, לא סיכם במהות.
מה הוא לא סיכם? עידו בייטי נגיד.
אני יכול לשאול, זה לא בדיוק מברוקס, זה ברוקס פלוס ספר פלוס סיפור. של בן אדם.
משתית של ניב.
נו, אז ניב ליטרלי. נו, אז מה אתה רוצה?
כן.
שכן, אני לא מבין מה לא מבין.
איפה?
7 ב'.
הוא העתיק.
לא, הוא פתר לבד, הוא ישב עם מישהו. היו להם ניסיונות אפילו.
סלח לי.
טוב, אתה במפיס כנראה סיימת, אה?
איזה סיימתי?
בדיוק עכשיו על
אני
השאלה עם
שובר את
ההזזה.
הראש, אבל אני עושה את זה, אז בוא נעשה, אני בדיוק,
רגע, אני חייב להשלים גם, אתה...
אני מנסה אבל שהפתרונות שלי יהיו ברמה גבוהה, אז אני שורף כל כך הרבה זמן על כל... כי אני אומר ממפיס זה הקורס, כאילו, ממפיס זה הקורס הכי קשה הסמסטר.
אפשר לי מזגן?
יש פה עכשיו איזה שיעור משהו? מזגן עובד עכשיו.
עובד?
כן. יש גם חלונות פתוחים, זה נראה לך את השני.
באמת נושאים, ואתה צריך להבין אותם, לבין שזה סתם משפט מפחיד עכשיו, ולזכור אותם.
Okay, it's 6, let's start. Come on. Okay, we're starting with the one body operator. Let's consider an example. We have the momentum operator P. Right? We know that if we operate it on a particle existing in the eigenspace with the eigenvector k, we get h bar k k. Now, if we have many particles in the system, we need to take this p operator on each one of our particles. We can say, if we have a very large state of particles, we can sum over all the pj for every particle j, get sum over h bar way. But this operator, which we can call capital P over a j, we can call it one body operator and simplify. Notice that a one body operator is not the same as saying single body operator. Single body operator means it's an operator that works only on one particle. One body operator means it's an operator that works on an entire ensemble, but in that ensemble it works on every particle separately. We can even simplify this further by gathering together all the electron, photons, whatever particles we have with the same energy k, and simply define this one body operator as sum over h bar k and k that operates on in k1 and k2 and so on, sum over k. Just to reiterate, I didn't do anything too complicated. I just took the single body operator that you probably saw in our Quantum 2 or Quantum 1 course. I applied it to a large ensemble of particles, and then I simplified it using operators we already saw in second quantization by basically gathering up all the particles with the same momentum into n and summing them all up in the k space. Of course, if you don't remember, nk is equal ak dagger ak. That's what we saw last tutorial. Okay. So this was a very simple example, but mostly it was very simple because I walked in the momentum eigenvector space. What happens if I want, for example, to walk in the non-eigenspace for the momentum? Well, I'm going to write the equation and then I'm going to explain it. For example, let's try to do this exact same process when we try to find the momentum, but in the position space. So in the position space, we know that we change marker. We know that P will be equal to minus I h bar. Good. Right? And I want to convince you that the one body operator of P here would be capital P equals integrate V to the Q R phi R P R phi R. Well, psi here are the creation annihilation operator in space. So what I'm doing here? Basically, I'm saying, okay, if I have a grand canonical ensemble of particles, all I need to do is find them, find the momentum of each of them, and then I get the grand canonical state. So what are we doing here? This annihilation operator with space basically says, look at a point in space. If there's no particle there, count it as 0 and ignore it. If there's a particle there, that's great. We find a particle, we can continue on to the next operator. Remember, we're walking from right to left. So I find a particle, I get its momentum by simply applying the operator, and then I put the particle back in. So all of this operation does for every space in our system, this is why we have this integral, is find the particle by finding out where we can destroy a particle, finding the momentum in that position, and then putting the operator back.
Just taking the continuum limit, basically.
Space is in the continuum limit. So
Yeah.
This is the same as saying a summation, but in space we are in continuous, so we have to integrate. Yeah, so this formula will be the same for every one body operator that we want to expand to space in a general sense. Okay. So, of course, we don't. This is a bit complicated. Maybe we can solve this and get a very simple and nice result for our momentum one-body operator. And I'll do it in the long way instead of the simple way right here. So, if you want to simplify from a non-eigenvalue basis to an eigenvalue basis, all you need to do is do a transformation. We know that to transform from position to momentum, all we need to do is do a Fourier transform. So, in space we have psi r should be equal to sum over k 1 over L 3 divided by to the power 3 divided by 2 ei k r ak. Very general transformation. And the conjugate 3 divided by 2 e to the minus I k r a dagger a k. Okay. Now just a small note. Sometime in the future I might not mention the L, like the normalization factor in the Fourier transform and such. As long as you're consistent, it's fine. Okay, so I'm gonna input our transformation into the equation. Equal sum over k divided by 2 e to the minus I k r k dagger minus I sum over k tag over half e to the I k tag of a k tag. Okay. Now, this grad will only affect this exponent, so we can do it. We're going to take this gradient in and order this equation a little bit better. Okay,
It's,
Hmm?
you wrote the wave function in terms of the ladder operators.
Mhm.
Just because it's like first order quantization, right? Not,
I wanted to transform from the space to the eigenspace of the operator.
no,
So it's transformation from R to K.
yeah, that I get, but the use of the ladder operators in the transformation is because we've proven previously that this is part of like first order quantization, right? It's not trivial for it to be
Okay.
an operator.
If we equate this to Fourier transform, this is like the Fourier components of the annihilation operator in space.
Sure, but you need to prove that it is the ladder operator. That it's some kind of operator, it's sure. But you need to prove it. It's not trivial.
Mm,
I mean, the proof just comes from the Fourier transform.
Right? But like Fourier transform just put it into the frequency / momentum space. The fact that the coefficient, which is what the ladder operator act as, is not necessarily the ladder operator. It is some kind of operator, a discrete operator that doesn't have to be. It's not necessarily on its face.
Oh wait, no, but the proof, it's actually simple. Look, the P, we established P is basically going to be the sum of all of the different momentum coefficients. P, J, all of them. And so, basically means that we're asking for the average momentum. That's literally that function over there. That's that integral. That's the average momentum.
a transformation of another operator will transform into another operator. If you do a simple Fourier transform.
Again, it's not a problem. The fact why it is the ladder operator. Like there is a lot of assumptions that are not addressed.
I don't really see the assumptions that I wrote.
For example, if we take another operator, would use not the wave function. You just take another operator, use the Fourier transform to transform it into the momentum space.
No, this is not a wave function.
What?
This is the ladder operator in space.
Okay. So it's just fine. Now I get it. Thanks. That was my problem.
Yeah, so
Okay, now it's clear.
if we continue, I'm just organizing everything here. I take the sum out and I leave only what's dependent on the space in the integral. So I have Daniel, tag, d qr cube e to the minus I k minus k tag r. This is just a delta function. We get, as we saw before, P equal sum over k bar k ak dagger ak. So after finish copying everything. So one body operators are very simple concept. You take an operator that we know that works with a single particle, and you try to apply it to an entire ensemble by summing over all the possible position, all the possible momentum, by summing over the entirety of space. Again, I want to clarify this is a single body operator, which means that it works on a single particle, one. This is a one body operator, which means it works on the entire ensemble, but every particle operates contributes only by itself. There's no like interaction between the particles. That's why we call it one body operator, even though it doesn't work on just one particle. And in the tutorial, there's also an example with of this entire transformation with the Hamiltonian, but I don't think we really need to do another one. There's another two examples with one body operator, but I think it's simple enough that we can skip it. Just doing exact same math with the Hamiltonian, with exact same math with spin. So unless there's any objection, I'm going to move to two body operators, and then we'll do a large example. Right. So what do we do if we actually have interaction? Let's see it by figuring out the free electron gas with interactions. Right. If we have some free electron gas, our Hamiltonian will be a very simple case of H0, which will be equal to sum over K, epsilon K, AK dagger AK, which is just the kinetic energy of all of the particles, plus VEE. Well, VEE will be the interacting term. So now instead of one body operator, we have interaction between pairs of electrons. I will write it very similarly. E sorry, R1, 2, VE, R1 minus R2, R1. Well, so again, so this just like the one body operator, we find every possible pair of two electrons in space. We extract the potential energy between them, and then we put them right back into our system. Well, of course, the potential energy VE equals to squared divided by R1 minus R2 absolute value.
That's second quantization, right?
Yeah, it's second quantization, but in space, so it looks a little bit weird. And now we'll move it to the ladder operator basis.
Shouldn't you make like integration twice, once over R1 and once over R2?
Yes. Usually when I write it like this, it means both of them. But I should write it explicitly. Right. So again, I want this operator to be written in the same language as the kinetic energy operator, and also the quantized momentum space. It's very comfortable for calculation, stuff like that. So I want to transform this potential again into the momentum basis, the momentum space. Right? So exactly the same as before. We transform P of R equals sum over K divided by L divided by 2 e to the minus I R aka dial, and of course the conjugate for the annihilation operator. And then I'll put this all in our potential. Equals there's also forgotten half here. So VEE equals 1 over 2 integrate cube R1 integrate cube R2 sum over K1 divided by L to the power 15 plus R1 K1 W 2 Dogger times okay, that was a little bit of writing. So all of it took the operator in the position space and transform it to momentum space. And now all I need to do is resolve these integrals. So again, when you do that, you take all the summation outside and try to leave only the part of the equation that depends on R1 and R2 inside the equation. So E equals 1 over 2 sum K1, K2, K3, K4, AK1, W, AK2, W, AK3, AK4, integral d cube R1 n cube integral d cube R2 L cube E minus I K1 minus K4 R1 E to the minus I K2 minus K3 2 V E R1 minus R2. Now the existence of this potential is very annoying as it's treating with R1 minus R2. So I'll do the transformation of R equals R1 minus R2. This will be the summation for the R2 integral. Alright, I'm just going to take the integral, I'm not going to write everything again. So after the transformation we have integral d cube R1 L cube d cube R L cube e to the minus I k1 minus k4 R1 e to the minus I k2 minus k3 R1 minus R times the E. Now I can integrate completely separately. I can completely separately integrate on R and R1. So we'll start with separating these two integrals. D cube R L cube of E I K2 minus K3 R V E R times integral d cube R1 L cube e to the minus I k1 plus k2 minus k3 minus k4 R1. The first integral, the integral on R1 will give us a delta k1 plus k2 plus k3 minus k4, and from this delta we can get the condition k1 plus k2 equals k3 plus k4. This condition kind of makes sense since we have to have a preservation of momentum. And we can define here momentum exchange using this conservation of momentum and define a parameter called Q, which is equal K2 minus K3, which we can also, if we put it inside our equation, our momentum conservation equation, we can also find it's equal to K4 minus K1. Okay. So, using our new momentum exchange term, we can even further simplify our remaining integral to be equal to, let me erase. I want to keep. I want to keep this equation for a reason. So using this momentum exchange term, we can put it into our equation. We have VEE equals 1 over 2 L cube sum over K3 K4 Q A K4 minus Q dagger AK3 plus Q dagger AK3 AK4 integrate over D to cube R, E, I, Q, R, V, Q. Now, VEE would just be E squared divided by R, and then this entire integration is known to be E squared divided by Q squared. And overall, VE equals E squared divided by 2 L cubed, sum over K3, K4, Q, AK minus Q, dagger, AK 4, AK 3 plus Q, dagger 1 over Q squared, AK 3, AK 4. And we transformed it to a relatively simpler momentum space-based equation, and we can see a very interesting little phenomenon that happened with this transformation. In position space, the entire interaction is local. We annihilate particle in position R1 and R2, add energy, and then put them back in the same position. But in momentum space, we annihilate two particles in position in momentum K3, K4, and then they're scattered through the entire momentum space by the Q.
Transference of momentum and not transference of location.
Yes. So one of them is local, the momentum, the position is a local equation, and the momentum is not local, or scattering, or yeah, an equation that describes scattering.
Is it like actually physical thing, or is it just like because we cannot distinguish between them, it is meaningless? Because they obviously move between location.
Yes. All this equation represent like an instantaneous interaction. So you actually don't physically move through position. You do get like exchange in energy and stuff like that, and which will later lead to a change in position. But in momentum space, the interaction actually does scatter basically a realm of possibilities. If you have two, for example, if you have two electrons with very known momentum at the beginning, after the interaction they will have an unknown location in momentum based on the momentum transition between them. And 635. All right. So I want to do an actual example. So let's take like an example of a system that you can analyze. This is some interesting method. So let's take a 10-minute break to 6:45, and then we'll do the Mott-Hubbard transition. Question. לא, שמע, א' כל זו שאלה לגיטימית, זו שאלה נכונה. אני אגיד שבתור פיזיקאים אנחנו כן עושים קיצורי דרך, אז כן להגיד שפרטורי סולם במיקום זה פרטורי סולם באתנה,
זה הגיוני, אבל בטוח שמישהו הוכיח את זה כמו שצריך.
נכון, אני לא ראיתי הוכחה שזה כמו שצריך. בין מיקום ומומנטום זה כנראה סופר קל, כי אתה יכול, אתה יודע שזה פשוט פוריה, אבל באופן כללי זו שאלה שצריך לחשוב עליה. אתה רוצה לעשות ממורה?
זהו, כי המעבר של רצף לדיסקריטי זה לא טריוויאלי בכלל.
אני חושב אבל שאפשר לעשות את זה פשוט לכל מצב, לכל שני בסיסים אפשר לעשות את זה ידנית. איך שעושים טרנספורמציה מבסיס לבסיס, לבנות את זה בעצמך.
אני לא אעשה את זה.
אני גם לא עשיתי את זה.
אני לא, בחיים לא אעשה את זה.
יש דברים שאני פשוט מקבל.
בדיוק, ממש.
ראית? זה הכל טוב.
סלק יש מוזגה. זה מישהו חי כתוב. אני לא... הסיכויים שלי הם בכתב, יד בטאבלט. אני לא...
אבל הנה תראה, זה כתוב יפה וזה אותו דבר.
מישהו סיכם על זה.
אני אשלח לך אחרי זה.
תשלח.
זה בבודל?
מצאתי את זה בדרייב.
העליתי את התרגול מודל?
זה לא. 3 לא.
לא טוב. אני חושב שפשוט מה שאני אעשה זה אני אעלה את כולם כבר וזהו.
זה
במקום
גם
להעלות
יכול
כל
להיות
אחד.
נחמד.
אעלה כבר את כולם ביחד.
אתה נמצא בקבוצה, אני אשלח. נמצא בוואטסאפ.
כן.
לראות כל פעם איפה החלק הרלוונטי ויש פה. אני נמצא.
Okay. Not about Transition. Let's consider a particular system. System where we have two potential wells, and we can fill them up with electrons. So we know that in this particular system we can have between 0 and 4 electrons. The interesting cases are the cases where we have, of course, 4 electrons, which mean the entire system is populated like so. Up, down, down. There can be no transition in energy, and this will be effectively an isolator. Another case is when we have 0 electron, and then there is again no possibility of transition of energy, and we have another isolator. So we want to find a third case where we have 2 electrons, which Hubble described as not isolated. Insulator, yeah. So let's define our system, and then we'll see what we can do. First of all, we have some interactional energy within the wells, which U equals to U, so over I, and I up, and I down. Basically says count for every position, for every well, count all the up electrons, all the down electrons. If you have 2 electrons in a well, they have some Coulomb interaction between them and they try to repel each other. So it's a positive potential. And we also have the potential of transfer, which is called HT, which we can define as minus T sum over sigma down, sum over IJ. Did you see? Did you see this sign for summation? This means yeah, I is not equal to J. I double sigma AJ double sigma. Or I'm not gonna write it explicitly. You understand?
Shouldn't it be not a dagger? The second
Yeah.
AJ.
Right. Basically, the potential of moving an electron from position 1 to position 2. Okay. So, if we have half filling, which means we only have 2 electrons in the system, we can easily plot all the possible states our system can take. It's basically 6 states. P1, which is 2 wells, did I define it with up or with down? Let's see. 2 wells with up. or P2, which has two wells with one down electron. We can also define a state when the two electrons are in opposite spin. So we have up, down, which we call S1. We just put cat on them. Also, of course, the inverse, down, up, for S2. Then there's the double occupancy states. Down. This will be D1, D1, or nothing, and up, which will be D2. You can check there isn't any other states. And now, if we want to analyze the system, the best thing we can do is try to find the eigenspace in the ground state. Only two states here are eigenstates of our Hamiltonian. Tell me which one?
The P1 and P2.
Yes, P1 and P2, because HU and HT will be 0. So it's a trivial ground state, it's a trivial eigenstate, but they are not necessarily the ground state. The ground state, we can assume, will have some combination of HU and HT. Note that it cannot be, for example, S1, even though S1 will give us an energy of minus T, of minus 2T, because if we operate the Hamiltonian on S1, the two electrons will flip position. So it has to be some combination of S1 and D1, and one of these combinations will probably also be a ground state, because we can potentially get a negative energy. And the energy of P1 and P2 is just 0, it's not negative. Let's try to expand a little bit on our state by writing down like so, and one up, and one down, and two up, and two down. In this writing, P1 will be equal to 1, 0, 1, 0. P2 will be equal to 0, 1, 0, 1. S1 equal to 1, 0, 0, 1. S2 will be equal to 0, 1, 1, 0. And I'll write it here. D1 will be equal to 1, 1, 0, 0. D2 equal 0, 0, 1, 1. This will help us in the near future. Now, Mott Hubble claimed that if we take U to be much greater than T, we can find another case with this half filling that we define right here, another case for an isolator. This is and this is the procedure that we're going to take. First of all, we can completely ignore the P1 and P2 state. They're already eigenvalue, eigenvectors of our system, and the rest will be only composed, must be only composed from S1 and D1. S1, S2, and D1 and D2. So we can completely ignore them. The most simple way to solve this, and I bet most of you can do it without me telling you to do it, is to create a 4x4 matrix of these two Hamiltonian and basically try to diagonalize it. By that, finding the eigenbasis. But this is only good if you have a 4x4. But if I take the system and try to add another well, or another 5, something like that, So today we're going to take this relatively simple problem and complicate it for fun. Okay. So our procedure will be as following. First, we consider U to be much greater than T. Like how. Then second, we consider HT, the transfer term, to be a small perturbation. We're not going to go deep into perturbation theory. We're just going to use it for one step. That's it. Then, based on this small perturbation, we'll do a canonical transformation. Transformation from H to H tag, which I'll define them after we start. And then this is please 4. We'll project our canonical transformation on the SI basis, since we know they must be dominant on our ground state. The SI basis must be dominant on the ground state because they're the term that benefit from the negative term. And 5, the effective ground state could be would be related to PS tag PS, where PS is the projecting operator. So step 5 and step 4 are almost the same step. Note that because of this projection, this method is really good at finding the ground state, but you lose almost all the information about your other eigenstates in the system. Let me know when I can erase the board. If you want me to repeat, because I didn't write the last step fully, I can repeat it.
What's the last thing you wrote?
The last thing I wrote is that we're going to take the projection of our transformed Hamiltonian into S space, and through that found our ground state. Have an approximation to our ground state. And there's an important note there, because of this projection that we do, we lose almost all the information on our excited eigenstates. Okay, so I want to start by defining the projection operators. Right. Yeah, okay. So projection operators does, as its name suggests, you take a vector, some arbitrary vector, and you project it into the basis that you choose for it. For example, PS SI will equal SI, PS DI equal to 0. And of course, if we have a combination of SI and DI, it will just give us the SI term. If we have, for example, 1 over square root SI plus 1 over square root of 2 DI, we'll get 1 over square root of 2 SI. So, if you look in our vectorial representation of our states, we know that PS of, for example, 1, 0, 0, 1 is equal to 1, 0, 0, 1, but PS of 1, 1, 0, 0 is equal to 0. And if you want to maybe guess how to write this projection operator in this simple case with the number operators? Okay. Yes. Equal to 1 over the half, 1 over 2. Sum equals 1 to 2. And I 2 minus. So if I have only one electron in each space, every n here will be 1. So we'll have 1 times 2 minus 1, 1 times 1. But if we have double occupation, so either n would be equal to 0, and this is 0, or n equal to 2, and then 2 minus 2 is 0, and we get nothing. But like that, we can project the combination of P and D into P space. Let's just check our work by, I don't know, multiplying by 1, 0, 0, 1. This right here and 1. This right here would be 2 equal to 1 over 2 with the sum 1, 2 minus 1 plus 1, 2 minus 1, 1, 0, 0, 1, 1, 0, 0, 1. I hope you will leave me enough so I don't have to show that it removes any D states, like 0 out of D state. And of course, I'm just going to rewrite it again up here. Simplicity 1 over 2 and 2ni minus I. And we can also write D term. D projection operator, and I minus 1. Yeah. This is the D projection operator. Now let's start with the actual method. And we have this. I want to define a seemingly arbitrary operator, f, to be equals 1 over pu, ps, ht, pd, minus pd, ht, ps. Now, this term, this operator is seemingly arbitrary, and also it doesn't really do anything that our Hamiltonian doesn't do. Basically, everything that it's, all that it says is take an F state, then do the T transformation, which means take an electron from one position and move it to the other position. It will necessarily turn into a D state, so somehow it seems like we have projection operator on the outside that really does nothing. But it will be useful. It's very useful because you will show in your homework that commutator F HU equal 1 over T HT. Which would be useful for our calculation. This, note that this F sort of describes the exact perturbation that our HT operator describes. So using F, we can do a canonical transformation for our Hamiltonian around this small perturbation using a Scheifer-Wolff equation. So H we transform to H tag equals e to the minus T F H E T F. this is a canonical transformation of operator under perturbation, or you will also see it as the time evolution of operator under Hamiltonian in the future. It's a very important equation. You should remember like the general form of it, and we can open it using Taylor expansion. Taylor expansion in second composition would look like so.
There's a name for it. There is a specific name for this kind of thing.
This entire equation is like Schaefer is. You can find it under a Schaefer-Wolf usually. Yeah. Although sometimes people only call this part Schaefer-Wolf. Sometimes people call this part Schaefer-Wolf. It's fine. It's all the same. Plus, if you want the name, Schaefer. Looks exactly like the normal Taylor expansion. Just a second. And since I consider t to be very, very small compared to u, I'm just gonna cut this Taylor expansion off up to the t to the squared. Any term above t squared, I don't care. So I'm gonna cut it off right here. So we only have this one, and we have this equation right here from before, which we obviously know it's correct because you're going to show it in homework. So putting this equation inside our system, let me just open it up a little bit more. Equals HU plus t minus t f HU minus t f HT plus t squared divided by 2 f HU. Note that I didn't add the third term with HT because it will give us t to the cube. I remove everything that's over to the square. All right, so from this delta t up here, we can cancel this out, and we can open this to be 1 over t ht. And I'm going to write and we're left with each time equals HU minus t divided by 2 f sig ht. Okay? Now we're going to do the final 2 steps together at once, and we'll start by projecting this. I'm going to start by looking at this term right here. I'm going to write it out explicitly. This is just opening the commutator. 1 over tu t PS HT PD HT minus PD HT PS HT minus HT PS HT PD PD plus HT PD HT. Yes. So again, this is just opening everything up explicitly. And now I want to project this entire thing into the S. Erased it. Into the A spaces, because we know that they will be the dominant part in the ground state. So I want to calculate hashtag PS. First of all, we know that HU on the S term will be equal to 0. So the projection of HU on S will also be 0. So we only left with a projection of this commutator on the S basis. And we know that PS PD equals to 0. Because they're autonomous. So we're left with F HT PS S equal to 2 divided by TU PS HT PD HT PS and the Hamiltonian that we want to calculate equal to minus over U PS HT D HT PS. Now this looks a bit weird. And in your homework, again, you will see that this entire Hamiltonian can be equated to this part right here, HT PD HT, can be equal to T squared 1 plus sum over sigma tag A1 Dariel, A2 Dariel, E1, E2. Yep. Sigma, sigma. And overall, this equation can be summed up as J S1 S2 minus 1 over 4. Where J is equal to 4T squared divided by U. Note that, in the final answer, the term that the final sign of potential energy is positive. So we get an anti-ferromagnetic distribution with the ground state that is mostly consistent of S terms and therefore is an isolator. Now, it might look like we didn't do much. We sort of excluded the D term almost completely. But this transformation, if we apply it, if we add more wells and apply this transformation to a very large state here, we can get the Ising model Hamiltonian with this method, which we will see later on in the course. And, yeah. We can using this method get a very simple long-range Ising model. Yes, this was the Mott Harvard transition. Any question? It's kind of weird. We kind of saw some new methods, some very basic and initial implementation of new methods. So
Outland have like a explanation, like to remind us how to do the.
Yes, also there's a bit more verbal explanation in the notes that I tried to do as much as I can in this in the tutorial, but yeah, Outland. If I remember correctly, Outland also have like a more general explanation of every term, not just in this specific example.
Okay, because I don't 100% remember.
You can ask question. You can ask question now. You can ask question after. Actually we come down with the tutorial, so you can ask question now or we can come.
כן, לא, אבל עדיף כאילו, אתה יודע, שלא ישאל אותך, טוב, תסביר לי את כל השיטה הזאת מאפס. אז אפשר לעבור על זה רבע שעה.
Alright, but no, that basically what we did is we defined, this is an operator that related to the perturbation itself, and then all we did basically was do a transformation around this perturbation, and then made some small assumption on our ground state that is mostly S states.
וגם זה מקרה פשוט, כאילו.
Yeah, it's a relatively simple case. Of course, if you see this Hamiltonian in the exam, which you won't see it in the exam, but if you do see Hamiltonian like this in the exam, you should probably just do it with the matrix.
Yeah.
With linear
algebra.
4 so. Yeah. Yes, this can be reduced by 4 by removing the p states.
יותר בטוח.
Yeah, it's safer, but of course the linear algebra doesn't scale well.
אף פעם לא. בעיה.
Scale as n squared. Yeah, that's the tutorial. Enjoy. Have a good weekend. כן, אני גם אעלה את כל התרגולים כבר. אחי, לא קשור לבית. מאחר. עכשיו הבית הראשונים פחות אכפת לי להתעכב איתם, כי לא חושב שאין לי שם פעם הערות להביא לאנשים, ולא אתה יודע, כל דבר צריך להשקיע. ועכשיו יכול להיות שהוא בית יותר רציני. אתה יודע מה? מוסיף עוד שאלות, במיוחד אליך. שרואה בית 1, שרואה בית 2, אבל יבין מי צריך לעשות. אז מה זאת אומרת? בואו נתחיל לזה. נסגר קראתי בשור החפסקי.